Hello, everyone, and welcome to today's OSA Technical Group webinar, Upconversion Nanoparticles for In-Depth Super Resolution Imaging and Ultra-Strong Nanoscale Optical Trapping. My name is Hannah Walter-Pylon, and I'll be moderating this webinar on behalf of the Optical Society. We're very excited to have Fan Wang from the University of Technology, Sydney joining us for this webinar, which was organized by the OSA Imaging Optical Design Technical Group. Before we get started today, I wanted to tell you a bit about our technical groups. OSA technical groups aim to create vibrant and active communities for all of our members to participate in. And OSA offers members more than 40 different technical groups to choose from, and each of these groups are led by OSA members who volunteer their time to organize activities tailored to your interests, such as today's webinar. And in fact, our technical groups have been hosting webinars regularly since 2013, all of which are available for you to view on our website now. So you can learn more about the technical groups, find out about our upcoming activities, and access our library of over 100 on-demand webinars by visiting us at osa.org/technical groups. Before we begin the presentation, I wanted to note that we will be addressing your questions at the end of today's talk, but we encourage you to submit questions throughout the presentation today. So you can do that by clicking on the Q&A button at the bottom of your screen and then typing your question into the pop-up box. You'll also be able to see questions from your fellow attendees in that pop-up box. And if there's a question you like and want us to address during the Q&A session, hit the thumbs up button beneath it to let us know. Finally, at the end of the webinar today, you'll be asked to complete a short survey to provide us with your feedback. You'll also be able to download a PDF copy of the slides from today's presentation directly on that survey page. This webinar is being recorded, and a link to the recording and a copy of the slides will also be emailed to you within 48 hours of the webinar. And so now it's my pleasure to turn the floor over to Zuzan Yang from our Imaging Optical Design Technical Group. He will tell you a bit more about the technical group and introduce you to our presenter. Zuzan, the floor is all yours.
Okay, sir. Can you see the screen?
Not yet. Oh, looks like now we can.
Hello, everyone. I'm Zuzan Yang from Cornell. I'm a colleague of OSA Imaging Optical Design Technical Group. Yeah, our group have the committee have Marina from Harvard and me as vice chairs and Anna and also Symmetria for our group. So our technical group is named Imaging Optical Design Group. Our focus is physics of linear optic materials, processes, drivers, and applications. We have 2,000 members. So our mission is benefit you all the members. We will organize some webinars. Also, we will do some social media publication and a technical event. Also, we will have some event in the conference. So you can find us in the website of OSA and also Facebook and also LinkedIn. So today talk we are so pleased to have Dr. Fan Wang from University Technology Sydney give the talk. And Dr. Fan Wang is an Australia Research Council DECRA Fellow and the US UTS Challenger Postdoc Research Fellow. He's working on the nanoparticles and biophotonics research. Dr. Wang has published over 56 peer-reviewed journal articles with a very high index of 27 and with more than 2,600 citations. Dr. Wang obtained his PhD from the University of New South Wales in Australia in 2014, and from 2013 to 15, he worked as a postdoc fellow in Professor Judith's group at NEO studying semiconductor nanowires. Since 2015, Dr. Wang joined the AS Center of Excellence of Nanoscale Biomechanics at Macquarie University. From 2017, Dr. Wang joined Professor Dan Yongjin group in UTS to lead the biophotonics team. From 2020, Dr. Wang joined the School of Electric and Data Engineering as a lecturer to establish his nano photoelectric group. Now he's individual group leader. And today's talk, he will focus on upconversion nanoparticles for in-depth super resolution imaging and ultra strong nanoparticle optical twittering or optical tripping. So, Fan, take it over.
Okay, thank you, Xu-san, for the introduction. And yeah, now I can share my screen. And let me, can you guys see my screen? Everything's
Yes,
fine?
you're
Okay,
good.
cool. Yeah, hello everyone. My name is Fan, and thanks to Xu-san and Hannah for the introduction. And it's my great honor to be here to present my work. And today I'm gonna talk about the application of upconversion nanoparticle in imaging and optical trapping. So I'm from Australia. I'm from the University of Technology Sydney. And for some people who don't know this university, I give a brief introduction. So this university is quite a young university, and it's actually ranked number 11 for the universities under 50 years. So it's quite high. And it's a young and good university. Location also pretty good in Sydney. It's a really good, got really good environment. So here is the Sydney. So it's in the south side of the Earth. And you see that it's like close to Sydney. There are lots of beach over there. And for example, we have the Coogee Beach and Bondi Beach here, all pretty nice. And the location of the university is right in the center of the Sydney. So we got quite a lot, really nice building. And it's also not far from the Opera House and the bridge. So it's really got a really good location. So when the COVID-19 ends, and if you got time and you're really welcome, come to Sydney, come to visit us. So my group focuses on the research for the material science, biophotonics, and also photonic devices. And today, because of limited time, I will only introduce the biophotonic side. So we're gonna talk about application of upconversion nanoparticle. At the really beginning, I want to introduce what is this upconversion nanoparticle and what's the special things about it. So upconversion nanoparticle is basically just a nanocrystal. You can see from this SEM image, there are lots of nanoparticles, size about like 50 nanometer. And the amazing thing of this particle is if you shine in near infrared light on those material, and it will emit release bright visible light. So if you mix this nanoparticle inside some film, like the figure, let me just if you mix this particle inside some thin film and put on the glass slide and just scan your mirror, you will see that really bright emission, and you can do the real time and just scan in real time 2D video displaying. So if you're talking about like the nonlinear photo response, most of people will thinking about some like second harmonic generation or third harmonic generation. So this is a traditional nonlinear photo effect, like you shine on the wave because of polarization, and then you have resonance, have a second harmonic generation come out. But the upconversion doesn't use this one. So we use a really actually is more efficient. Yeah, in the nanomaterial, actually, this one is quite efficient. They use the energy transfer system rather than the nonlinear photo response. So what I mean is like inside this nanoparticle, they have sensitizer to absorb a near infrared photon, and they have advertiser to give the emission. And then they have like multicolor emission, and inside this nanoparticle have some energy transfer process. If you look at the inside of this particle, they have the ytterbium to absorb a near infrared photon. And because the energy gap is directly matched with the near infrared, therefore the absorption is linear. So therefore the absorption is really, really strong. And then after absorb the photon, the carrier will pass the energy to another side, which is the emitter. And then this passing process is nonlinear. And after this one, they have the emission come out from the all different energy level. And the really good thing, the reason why this one have really high upconversion efficiency because they have many levels. So each of these real level will give you high chance to, like each of them is a metastable state. So the carrier have longer lifetime in each of level, then they will waiting for another carrier to come in and pump the energy to another level. So it's just like catching on some ladder. To a traditional 2-photon absorption, you don't have this real level, so your chance is really low. But for this one, sorry, excuse me. But for this one, because there are many real level over there, so therefore the chance is really high. So this is why this nanoparticle got high upconversion efficiency. So sorry about so much formula, but I have to show this to show you what's the fantastic of the energy transfer system. Because inside this energy transfer system, there are many interesting parameters here. So for each of the level, they have one rate equation. And there's one really interesting term, which is this K, which means cross relaxation. I'm gonna explain this really soon. But this cross relaxation will help your carriers fastly build up like a photo avalanche effect. And this will give you really high nonlinear effect. And apart from this, if you look at all the energy levels, they are all in relation to the carrier number in another energy level, which means that with at the higher energy level have more photon effect, like 5 photons, 6 photons. And if you include all of them, you will see that those give you a super linear effect. And also this doping, this C is the energy transfer constant. This one also in relation to your doping concentration. Once you dope the more carriers, more emitters inside this material, and you kind of decrease the spacing between each of the emitter, and this will also change all of this constant. So which means like all the response is like manipulatable. So for example, in this figure, you can see that as we dope the different concentration, you can change the photo response curve. And you can change it from the traditional like 2-photon like structure into like the more photon structure. Also, they look a little bit like a lazy LL curve because they also have photo avalanche effect. And you will recognize it will also have some saturation. So this saturation also really useful because they only have limited emitter here. So you can really easy to achieve the, because high efficiency of the pumping, so you can really easy to achieve the saturation on the emitter. And it's also got multi-energy level. So this is all about the property of this upconversion nanoparticle. And so based on those property, those nanoparticles have really strong anti-stock emission and have multicolor. For example, if you change the dopant concentration, if you change the dopant like erbium and also the thulium, different type of material, and you can also select different emission band. You have like multicolor. So for example, this one from Xiaopeng Liu's group, they can do the 3D display and with full color. And because it's atomic transition emission, so doesn't like the dye or the quantum dot. It doesn't quench, doesn't blink. So it's really stable. So it's really good for trapping, for tracking the single nanoparticle. And it's also really uniform. Each of them, the size distribution and the intensity distribution is really, it's really uniform. And also they have like several really good property like dual near infrared band. So because the emission and the excitation all can be near infrared, also have nonlinear response and have the cross relaxation. So these are all the properties of this nanomaterial. So this is the reason why we plan to use it in our imaging side or optical trapping side. So today I'm gonna describe the application from 3 sides. Deep tissue super resolution imaging, optical trapping, and single particle tracking. So first of all, I'm gonna mention about the super resolution imaging. I think most of you already know this technology, so I'm gonna just quickly breeze through. So traditionally, because of diffraction limitation, we couldn't see the features below 200 nanometer really clearly. Until 2014, Eric, Stephen, and Mona, they developed a super resolution microscopy. With this one, we can see the features below 200 nanometer clearly, and this helps us to have a much better understanding what's the fundamental of the life. So there are already many super resolution technology over here. And for me, each of these technology just like the different character in some game, like some Three Kingdom game, if you recognize this figure. And the reason why I see similarly, because inside the game, all the characters have different ability. And in the super resolution, they also have different ability. And so we are looking for good resolution and better working depth, and also biocompatibility and long-term and high speed. So we want all of them. And so for example, static traditional super resolution technology have really high resolution, but require really high power. Storm also pretty good, but a little bit slow. And recently combined with machine learning and other technology, the speed is already rising up, but it's still not like really fast. And the same is a really good one, structured illumination microscopy. So if you combine with nonlinear SIM and also Hessian SIM denoising method, you can have a high speed, high resolution, but the working depth is also still limited. So if you look at all the major technology, they all have limited working depth. So this kind of is the current limitation for most of the technology. So what we want to do is we want to use our near-infrared probe to solve this problem. Because if you have both excitation beam and also emission beam in this first biological window, you pretty much can have like longer penetration depths. And once this happens, you're supposed to have a super rise with longer penetration depths. So for example, so this is one video from Professor Das group. Hang on. Yeah. So you can see that if we put lots of this particle inside a mouse, and then you can see everything clearly, and it's almost background free. So it's really nice. And what we want to do is exactly same as this one, but we're gonna do superrise. And now the question is, how can we do superrise with this nanoparticle? Because there's no available method to doing that. So first of all, we're thinking maybe we can use this cross relaxation to doing that. And so the cross relaxation means if we have so for example, if we have carrier in the top of level, when it's, let me open my laser pen, and yeah, if we have carrier in this level, when it jump down to the intermediate level, the emission photon will match with the band gap with another one from intermediate to bottom. So therefore, when one jump down, we'll at the same time excite another one to the medium level. So therefore, with cross relaxation, it's really easy to accumulate the carrier in the intermediate level. So therefore, once we form like a population inversion in the intermediate level, you just need a little bit like a light to trigger this one to match with this intermediate emission wavelengths, and then you can trigger all of them come off. So this is a stimulated emission. And so when you don't have carrier in this intermediate level, you kind of cut that ladder. So you couldn't have any emission from the top level. So you kind of just switch off your emission. And this one is really efficient because you use a stimulated trigger everything off. So therefore, we published this paper. By the way, Xu is over here. So Xu is the co-first author for this paper, and we just use the wavelength of 1800 to match with the intermediate level, so we can trigger everything off to turn off the emission, and in the middle we can maintain this laser, and then we can achieve really high efficient stat. So just need like tens of milliwatt power, and we can achieve like a really good resolution. And currently we achieve like even more better resolution compared with this Nature paper. And but the challenge is for that one, we just use instead. And we still have really complex equipment. So we have actually, if we using the superlinear effect of the upconversion nanoparticle, we also can generate another really straightforward super resolution technology. So in 2019, Arthur published one paper, theoretical paper, described this one. So inside this nanoparticle, because we have like really interesting energy looping, I won't go through the process here because of limited time. But generally, you can think some of the photon will be reused in some energy transfer circle, and then your photon effect can go to like even like more than 10 or close to 20. And with that one, if you matching with some certain wavelengths and select the certain range of power dependent curve, for example, like this figure, so your power dependent can be really, really sharp. And using this one, select a certain range, you can just by directly scanning, you can have really high resolution. And in 2019, same year, both our group and also the NISA's group, the NISA published one paper experimentally showing this kind of effect. So it's showing that if we just put this particle inside living cell, and by select the pumping laser in the certain range, they can directly resolve some things here. So so they can directly see the supervised imaging, but the resolution is not that good, so only 200 nanometer, but it's already supervised. And for us, we saw the same thing. So once we decrease the excitation, decrease the excitation laser and to match with the condition, we see that the resolution of the image can go down to like 130 nanometer. And most interestingly, we also seen that if we combine with the STAD, so if we look at STAD, when we decrease the excitation wavelengths, we also found that the resolution can go down to really, really low. So it's really good. And this is interesting because when you decrease the excitation power, you pretty much just manipulate what's the energy transfer rate. You pretty much just decrease the pumping rate. And for this one, actually, you just control the energy, the carrier distribution in the top level, and then you pretty much enhance the depletion efficiency. So this is why we have this high resolution here. So we've seen that the two resolution just synchronize when excitation power goes really low, both of them showing like high resolution. But we still have some challenge, which is we did use this one to achieve the super resolution, but their emission still visible. It's the blue light. So we couldn't use this to expand our image depth. So we needed to change this to the near infrared emission. And for doing this one, we're actually thinking we can use this saturation to achieve one method to use this supervised. So for this method, the setup is really simple. We just need to generate one donut beam. And using one donut beam combined with this saturation, it's really easy to achieve super resolution. So what we did is we shining a donut beam on the sample. So this is a single nanoparticle. And once we increase the power, because everything will be saturated, and then you will see the middle hole come to smaller and smaller. And because the 800, if you still remember the previous we discussed about cross-relaxation, the 800 energy level got the population inversion. So it's really easy to be saturated. And we just need to use a small power like a 50 milliwatt or even 10 milliwatt. We can saturate the material and we can achieve like a really small hole in the middle. And so this gave you supervised information. And we try to put this particle inside a deep tissue like 900 micrometer tissue. And we can see that for the blue light almost fade off, but the 800 emission will keep here. And if we just use a donut beam, and you can see there's a small delta in the middle, probably too small for you to see. Oh, sorry, just wrong click. Yeah. So you see that there's one hole in the middle. So over here is basically the single nanoparticle. And the amazing thing is once we increase for different thickness, and we always can see this hole in the middle. And by just increase a little power about to like, for this depth, almost like 80 milliwatt or something. So you still can see clearly single nanoparticle here. So the PSF, the the resolution of this image is still maintained the 50 nanometer. So if we put some particle inside this deep tissue and sort of confocal, near infrared confocal, we can see the particle, and with the superride, we can resolve, and with deconvolution, we can still solve this particle. So which means that we can achieve superride 50 nanometers through this 100 micrometer tissue. But it's still not enough. The reason why is, apart from just look at something through the tissue, we're also interested into research this kind of sample. So this sample is called organoid. So it's really hot recently. And I think 2 years ago is the method of the year for the Nature method. So basically describe one method to generate the man-made, the mimic of the real organ. So it's got similar function. So for this organoid, it's got like a lot of cells inside. The cell density is really, really high, almost 4 times higher than the normal tissue. It's more like you cut some layer of meat, squeeze it into a bowl, and therefore the scattering is really, really strong. And if you use our prism method for this one, it doesn't work. I mean, it's work, but it's work for only like 20 micrometer, won't go through like 100 micrometer. So this is why we want to expand our method a little bit to make it to work on this organoid sample. So what we did is just combine with the basal beam, and our collaborator from Peking University, Shigobin, did similar things, but it's for STAD. So over here, I want to introduce the basal beam. So basal beam is some like interference-based beam. So it's really interesting. So all the beam, when they come through this hexagon or something, they change the angle, and the focus is by the interference of the different direction of the beam. And the amazing thing of this beam is if you block some part of the beam, doesn't matter, because the rest of the beam will still propagate, and they still have some interference in the focus. So which means that if you have some object block or disorder some of the beam, doesn't matter, it doesn't change the focus. So which means that if you have some like a 1 micron sphere or some sphere block part of the beam, and in the focus it's still gonna have a nice donut shape over there. So this is a basal beam. And what we're doing is just using the basal beam and combine with the LJ beam, the donut beam, and then we can do the superrise inside this organoid. And for the selected area like this, we can see this emission. And if we zoom in and doing the supervisor deconvolution, we can see lots of nanoparticle. Only slightly limitation is that the XL resolution is still just a confocal resolution. And we are working on that to improve. And we pretty much can use the depletion to solve this problem. So this paper published in Small. So after that one, we looks like we solved the problem for the depths, but the problem is like this one is really, really slow because you base it on single point scanning. So 1 point by 1 point, if you scan like, if you do the superride scan the whole organoid, like 100 micrometers take ages to finish. So this is why I want to introduce another method. So this method is really powerful. It's a structural illumination microscopy. For I'm gonna still briefly introduce this technology for someone who not familiar with this one. So the structural illumination technology is a method to play with the frequency domain and to increase the image resolution. So if you have your sample here, and if you just use some finger pattern shining on the shining on your object, then you have the beating of the pattern with your object. And if you analyze this information out, you're able to just solve the frequency of your object. So in the mathematical domain, you can think if you have some pattern like sine wave or something shining on your object, you kind of like push your k vector in another direction. So if your finger is the diffract limited finger, it can push the k vector to the edge of the k space. So this is in k-space image, and so this ring represents your resolution or the ability in k-space. Larger pattern in k-space means like higher resolution, and just from the Fourier transfer. And once you have the middle point here and you use this pattern shining on your sample, your emission gonna be like something like the pink one. And so once you solve the equation, once you get the image and you can solve the equation, and finally you can have like, you can get this 3 pattern, and in third domain, you can put them together. Then you can kind of extend your observed error in your k-space. And if you rotate your angle for several different directions, then you have the full image. And this will cover everything and give you the full resolution. And slight limitation is you can see that your resolution will only increase by twice, because this K only can go to like twice of this size. So to further expand the resolution, they have one method is called a nonlinear sim. So this nonlinear sim is really interesting, because even you use this like pattern sine wave shining on your object with certain frequency, but if your sample have nonlinear effect, it means that your emission pattern maybe have like more sharper information come out, because for example, if you have saturation or something, and then you're gonna have a narrow depth inside, because everything else will saturate, same as what we use in the donut beam. And so which means that if you have nonlinear response, you have extra resolution. So more specifically, if you have like a high harmonic generation, you can push your K vector to another level, like the yellow ring here. And if you have like one more order nonlinearity, you can see that in Fourier domain, you can solve the equation to push your vector even further. And if you're doing that, your resolution can be really, really high, can down to like a 50 nanometer. So only challenge is, if you want to trigger this nonlinear effect, usually you need to use really high power, and for SIM, because it's wide field super resolution technology, so it's really hard to use really high power and trigger all this kind of nonlinear effect. And so this is the reason why we want to use our nanoparticle, because for our nanoparticle, you just need to use tiny bit of power. Actually, you can have really good nonlinear effect here. And this power-dependent curve means that if you shine in some pattern onto a nanomaterial, the response can be different. It would carry more resolution output. So yeah, and another benefit is again, because the near infrared emission. So over here we have one test. So we use green laser, green emission and 800 emission, and without tissue, you can see both of them have nice finger output. But with tissue, because the absorption, you will see that the green light you couldn't see clearly the finger. But with this one, you can see with the 800 emission color, you still can see the finger. And if you look at the frequency domain, if you're shining some pattern onto your material, and then you have this response, and in the spatial frequency domain, you will see that if we increase the doping concentration, you pretty much increase your nonlinearity, and therefore your high harmonic peak over here is like first, second, third, fourth order come to even fourth order come to really, really high. And so which means that in this material, it's really easy to achieve high harmonic emission. And we're gonna use this to achieve the same. And only one limitation is for this nanomaterial, the 8% doping one, you also need to use high power. So for a component, and for our power laser, we only have like a 500 milliwatt power in focus, probably only like less than 100 milliwatts. If you expand the beam into like a 20 micrometer or some larger spot, your power density is really, really low. Usually just 100 kilowatts per centimeter square. So this is why we use this 4% Serlim one. And for the power dependent range, we basically just using this one. So over here, so yeah, we didn't use the saturation because it requires really high power. So it is just the left upside. So if you're using this one, this power range, we can achieve like really high resolution. So, so this is some of the result. You can see that we can see lots of nanoparticle. Again, this one is like using this one, we can achieve like through the deep tissue, like 51 micrometer thick, but with a much faster rate. And for the error can be like 50 micrometer or 30 micrometer, and the resolution currently 130. And by changing the property of the particle or make a core shell or something, we can further increase the brightness. In other words, we can increase the intensity, and we can increase the resolution. So this one just published in Nanoletter. So upon this work, another interesting thing we can do is we can do some time resolved thing. So our PhD student Jiayan make some really good sample over here by changing the doping concentration. Actually, she can co-dope several different elements. And once we play with the energy transfer inside, we can control the lifetime output. And once we can control the lifetime output, we pretty much can generate lots of samples with different emission time. And so for this part, if we use this particle in our sim, we pretty much can generate a time resolved sim. So there are some samples showing that if we put in nanoparticle over here with a different time, like you can see this time frame and your emission is different, which means that if we have several, so for example, we pick the number 1, number 7, or number 3, we pretty much basis on the time response, we can do the multiplexing imaging with the same and with only single types of nanoparticle. If we combine with the wavelengths, because currently we can, so for this one, we only need one wavelength. If we combine with wavelengths, lifetime, we can do the more multiplexing things. And one example is here, we put a 3 type of nanoparticle here. And with the same, we actually can resolve them previously because like if you use wet field, you couldn't see clearly. So some of the particle will mix each other, but with same, you can resolve the two. And also you can distinguish of them. If we, in future, if we can use this to label some biosample, we can do the multiplexing time resolve the same. So I also want to introduce another method also working for deep tissue, which is multi-energy level. Apply the just using the multi-energy level to achieve the supervise. So for this method, we're gonna use the photo response for different level because as I mentioned before, for different level, they got a 4 photon and 3 photon, 2 photon effect. All of these photon effect have different response, even with the same doping concentration. And what we're saying is if we shine in one excitation beam here, because of different response, they can have different PSF output. So this is really useful. The reason why is that currently there are already many of PSF engineering technology, for example, the subtraction, and also from Professor Liu Xu, the Fourier fusion, and also the stepwise. So there are many methods like process of the different type of image and give you higher resolution and also give you like less artificial, but they all need 2 times of scanning. But with this one, because we have different response, so we can if you use dichroic mirror and we can detect the 2 types of image or 3 or 4 types of image at the same time. So this is super useful because if you generate all of them at the same time, you can do the real-time processing. You directly save half of the time. For the stepwise, you need like 5 or 4 image, so you even save like 4 times of time. Yeah. So so this is some result over here. If you use like the 90 excitation for the 800 and the 741, you have Gaussian like output and you have donut output. In the Fourier domain, they are different. And if in the Fourier domain you do the Fourier fusion, you pretty much combine all the high frequency things together, you have like much better resolution come out. And this one compared with the deconvolution method have less artificial and still maintain the really good resolution. So we do use this method to resolve some complex pattern. You see the supervised, the panda, we organize the particles into some shape. And over here is for this flower, or somebody call this a mooncake. So yeah, So for this mooncake, you can see the advantage of this method. So if you use the deconvolution, you will see lots of hole in the middle, and you do have higher resolution, but you see we got many artificial things here. You couldn't use deconvolution to get this one nice picture out. And for the Gaussian, you can see the general shape, but you don't have really good resolution. And by doing the fusion, we actually have really good resolution. And at the same time, we can see everything clear with much less artificial effect. So this kind of is the supervised method I want to introduce today. And the next, have a little bit of time, I'm gonna quickly go through the single point tracking and also optical tracing. So for single particle tracking, there's like a really, so it's a really old topic. There are many methods, but there are still like some room of that still to be developed, because we need for all the method, the challenge part is like you need like a really simple, really fast, long-term, no background, and also you want to distinguish which is a single nanoparticle, and you want to naked eye visible sensitivity. So the mean by this is usually if you want to detect the image, you need to use a really large sensitive EM CCD to do the single particle tracking. But in future, if you want to transfer this into some portable devices, you couldn't wear this big camera with you all the times. So you need something, you can use your phone image, phone camera, or even your naked eye, you can track in, you can see this single nanoparticle. And another thing is like to have, so for example, for this one gold particle, if you want to distinguish the single, you need to analyze spectrum. So it's also take a long time. So what we want to do is just make some super easy method to do that. And over here, so the figure you've seen that is each of them, like some of them is not single nanoparticle, and from the brightness, you can also tell which one second, 2 nanoparticle, 3 nanoparticle. And I want to mention for this video, it's just a really low cost camera, only like tens of dollars. If you just use, you can use your mobile phone. If you want, you can also use your eye to track in this single nanoparticle, because the emission is really bright. And also from the emission, because the emission is really uniform, and from the intensity, you can also check which one is single, which one is not single. Once we know that, it's quite useful because we know the size of nanoparticle, and then each of particle just like a car in the traffic, and you can analyze what's the speed, and you can analyze what's the MSD, and once we know the size, we can go back to calculate what's the viscosity. So this is gonna be pretty useful because you can see that these two particle, we can see from previous image, these two actually is inside the nucleus of the cell, and those three is outside nuclear cell, and the P3 for this phase is actually goes through the microtubule. So you can see that for different type position, you can map out what's the viscosity. And because the power dependent, we can also do the multiplexing. So by controlling power, you can see different type of particle even for same color. So which means like apart from time, color, we also have power can play with the multiplexing. So one more thing I want to mention about the tracking is like we also can through the PSF engineering to achieve some interesting high resolution tracking, XL tracking. Because for XY, you can just use location to analyze, but for Z, you can modify the PSF. And we found one really efficient way to modify the PSF from the single emitter, so which is a self-inference. If you put some emitter on top of mirror by controlled spacing, all the emission will bend off interference by itself. And for different dipole, the interference pattern is quite different. For example, for this one, if you have the destructive interference, you're gonna have a hole in the middle of the PSF. And if you change the different spacing, this pattern will be gradually changed. And this change is really sensitive to the position you gave. And it's not sensitive to the state. So it's only sensitive with the position between the emitter and the mirror side. It doesn't sensitive to all the drifting, this kind of things. So therefore, we can use it to do the distance sensing, and also we can use it to do the tracking. So for example, if you put all this particle inside some stepper light, and even just a 10 nanometer different, you will see the PSF from like a Gaussian-like beam and jump to a donut beam. And by doing the calculation, but actually from different feature change, we can resolve sub-nanometer change of the height. And we actually can put this into some tracking. We put one particle into the glosser, and you can track, you can do the supervised track of them. And I mentioned before, this method, because it doesn't matter the whole thing drift or not. So basically, it's a drift-free method. For other methods, if you focus the drift, you kind of like got the wrong information. But for this one, doesn't really matter. So this is one example. If you put a particle here, you see the PSF change with this move in the z-axis position. So finally, I think I still got a little bit of time. I try to be faster to describe this one, the nanoscale optical manipulation. So Hannah, how long time I still have? 5 minutes or 10 minutes?
You have about 5 minutes left.
5 minutes, okay. I try to be fast, okay. Yeah, so nanoscale trapping is kind of really interesting one. So for the really inside of the really range, if particle really small, it's basically fitting into the really range, and then you have the gradient force and you have the scattering force. And if your scattering really strong, it will like laying down your trapping potential, and the particle is really easy to pump out with the laser propagation direction. And yeah, so this is one example. We can trap one gold nanoparticle, 50 nanometer, and we can move it really fast. And but the challenge is you need to use really high power. So for this one, we pretty much use like 100 milliwatt power, and so this is quite a lot. So in relation to nanoscale trapping, so with this, the one parameter of the polarizability is really important, because we can only trap things, traditionally we can only trap things with the contrast of the suspectivity or the, hang on, let me open this one. Yeah. So you can only have a contrast of the polarizability, or you have the contrast with the permittivity. So this one, your material, your surrounding material usually just water. So if your particle have the same refraction index, you pretty much couldn't trap them. And so for your gradient forces, so that is the trapping force, actually is in relation to the real part, and your scattering is really in relation to the amplitude. And the scattering matter because you want to see some scattering to detect the trap stiffness. And the challenge of nanoparticle is for gold particle, it does have like a higher value, but it needed to be, the trap stiffness is not that high. So you still need a high power, and then you're pretty much heating your surrounding biological sample. And if the size is going to really small, actually scattering also quite small. Another candidate is the semiconductor nanoparticle, but the trapping force is also limited. For upconversion, actually the refraction index is really low, so the trapping force is actually really small. But we've seen that actually for this nanoparticle, even single one, it's really easy to be trapped and squeeze into a cell. And not only our group, we've seen that there are lots of other groups can doing the similar things. Also, because this particle have temperature sensitive emission, so you can actually use it to do the temperature sensing. So this is amazing. And most of people doing this one, but there's the like question that why we, so if you look at the previous image, so the refraction index is really low. So why we seeing this strong effect, people still don't know. And one problem is like, for say, people don't have like a really good method to detect the trap stiffness, because scattering really small for this particle. And we designed one method to showing that combined with machine learning, we can do the 3D trap stiffness detection. And we first saying that for this upconversion nanoparticle, got huge trap stiffness compared with even gold nanoparticle in same size, 30 times enhancement. So this is amazing. And currently, there are several hypotheses to showing why was the reason. One is the photoelastic enhancement. So this is about the surface potential. If you have lots of surface charge, and all of them will increase the polarizability. So Daniel mentioned of this, but it doesn't work here because we did some experiment. So if we use the same zeta potential particle, but the trap stiffness is also different. And from the Daniel theory, basically, if you have like different same zeta and even different size, smaller different size, your trapping force should be same. And another thing is gonna be the almost round of power, round of the time. So yeah, so another one should be the radiation, the deuterium force. But with this one, I did simulation, doesn't match, doesn't give you 30 time enhancement, and also doesn't belong to the super radiance. So Paris literature showing that this will give about like 10 times enhancement. So what we're seeing here is actually the ion resonant. So this is really, really interesting. It's basically if you have the electron field, you push the ions, the electron crowd into another thing. So it's kind of just a polarization. But in this material, because we have like a stack level, multi-stack level, so this really help because if you look at the permittivity, if you look at the suspectivity, all the dips is balanced with the peak. And because of limit time, I won't go through the detail. But anyway, so this one combined with the 3 stack value is actually give you really high, like if you match it with the resonant condition, but off a little bit from scattering condition, you can achieve like really high refract index. And using this one, we do some simulation, and we can see that with the size increasing, your force is like keep increasing, and because we increase the polarizability. And you will also see that when the particle smaller, like smaller than 10 nanometer, and your zeta force or the surface charge taking charge. But if like larger than this one, so your ion resonant force is like directly come to really, really high. So with this one, we can even trap the particle inside some like a solution with the refract index just match each other. So this is amazing because previously we couldn't trap anything without any refract index contrast. And another thing that's really interesting is once we achieve this one, because this nanoparticle can be used just like dye, you can use it to label single cell. So you can use this to label inside cell or outside cell. Once we're doing that, we can increase the first interaction with the cell. So it's kind of novel first probe. Like this one, we can, after we coating this nanoparticle, the speed can be increased even twice. So because the first increased twice. So this kind of today what I want to mention, basically about superrise, we mentioned about the near infrared acceleration microscopy, organoid imaging, and we're talking about viscosity sensing. We're talking about the high force of the nanoparticle. So I'd like to thank my team, my student. So also Chao Hao just graduate, and Xuchen Baolei, Yuntao, they all almost graduate. And I also want to thank my collaborator, Da Yongjin, for providing the nanoparticle, and Peter Reis and Jack Atish. So yeah, I also want to say that I currently have some PhD student scholarship available. So if you're interested in doing on-chip superrise and biological laser cooling or superrise characterization, please send email to me. So thanks for your attention. And sorry about the delay. I think I delayed for a couple of minutes. Yeah.
You're great. Thank you very much, Fan, for the presentation. So we're going to move into our question answer session now. So if you have a question, please go ahead, enter it in the Q&A box. And you can also vote for your fellow attendees' questions by clicking on the thumbs up button if you see a question you like. So our first question came from Ram Subedi, and he had a couple questions for you. So I'm going to take them one at a time. His first question was, could you shed some light in absorption mechanism of the nanoparticles? Is multiphoton absorption relevant?
Sorry, the question is about the absorption of nanoparticle, right? Oh yeah. So So the basically is it's a turbine ion, so it's more like just atomic absorption. So you know the rare earth element, their energy level is more like just matching with the near infrared photons, about like, so matching with 975, but the absorption peak is really narrow. So generally you can, I think if you look at, so there's lots of literature saying about this one absorption, because these rare earth elements have been well used to make laser, solid state laser, or make use of fiber laser. So absorption peak is the reason is a little bit narrow. So I think it's from 941 to like 986 or something like that. So yeah. But compared with the semiconductor and also die, the absorption peak is not that wide. Yeah, but the efficiency is high, but not as high as semiconductor. But the thing is like it doesn't quench. So because all the atomic emission is quite good. Yeah. Did that answer the question? I'm not sure what specifically he asked about the absorption. Yeah.
Okay, hopefully that answers their question. We can move on to the next one, which asks, how would upconversion benefit if 800 nanometer light would work the best during the imaging process when compared to blue or green?
Oh yeah, this is a really, really good question. Yeah, because we know that like for longer wavelengths, actually the emission, the resolution is not really good. So it's kind of like we take some advantage, but we couldn't. Yeah. So for us, definitely the wavelength is limited or resolution. This is the truth, but we can compensate with nonlinear effect. So for example, for the stat one, so we do have limitation on the resolution because the donut beam we generated, the full wave half maximum is not that narrow. But from the linear effect, like saturation one, we also from the power dependent, we are really easy to like use smaller power achieve like a narrower emission point function. So we kind of use other property to cover this disadvantage. Yeah, but yeah, I mean, if you use visible light, you don't have this kind of long penetration depth. So I think this is some balance you need. Yeah.
All right, great. So then they had a third question for you, which asked, power of the excitation energy in terms of milliwatt was mentioned in the presentation, but the power density might give more information of the intensity of light used. Could you comment on the spot size of the laser excitation source?
Yeah, sure. So for different technologies, slightly different. So for the same one, under the tracking one, the excitation power, I mean, the power density is really, really low. I think I forgot it's showing on the paper, but mainly about 100 kilowatt per centimeter square. So the power density is not that high. But for the confocal side, it's a little bit strong because our beam spot is about half of the wavelength. So it's a diffraction limited system. So it's about the, I think power density will come to almost a milliwatt megawatt per centimeter square, because our beam spot is like a half micrometer for the diameter, and the excitation can be like 50 milliwatts. But the thing is like, because we use the near infrared light to shine in our sample, so actually this gives us lots of benefit. What I mean is if you use green laser 50 milliwatt or even just 20 milliwatt shining on your cell or biosample, it will die immediately. But if you use a near infrared, so in the paper, I think in the light paper and in another one, we did some experiment. We used like 80 milliwatt power of the beam and near infrared shining on focus into a single cell, and I think with 1 hour or something still live. So the reason why is because the cell doesn't absorb much about these wavelengths, but this wavelength does. If your power really high, you does heat up the water, so that will affect the cell. But the cell doesn't absorb much with these wavelengths. Yeah.
All right, thank you very much for answering those ones. We'll move on to the next question, which came from Faye. and asks, how would you verify the multiphoton emission process and determine the order of the nonlinearity?
So that's a super good question, because in the community, lots of people just using fitted by if your slope is 4, that's 4 photons, slope is 5, it's 5 photon. But in our community, I mean, in this material, it's not totally correct. If you, I couldn't show the PPT, but if you remember the rate equation over there, so usually 2 photon or 3 photon, you just rate equation equal to n square or n 3 times power of 3 or something. But here it's more like you have from n power of 5 plus n power of 4, n power of. So in the rate equation, actually for one level, it combines all of these different power ratio of the carriers. So it's like even for 5 photon energy level, the emission will, the power dependent won't be a nice power of 5 or something like that. So it's really mixture one. And so how to qualify how many photon? Currently, to be honest, we try to match. So firstly, we need to use the simulation. So we do the rate equation and calculate what's the power dependence curve, and then we try to fit with our experiment model, the power dependence curve, and then we can solve them. Unfortunately, because for the 5 photons, 6 photons, they're all different. Like the power dependent curve is all different, really easy to distinguish. But there are some so from theoretically, if you use other wavelengths, so for example, from UC Berkeley groups, they use 1064, and they can trigger energy looping, and then N can be really, really high. So for that one, what they did is doing the same thing, just doing the modeling and then theoretical modeling and doing experiment, try to match of them and then try to give them. So a little bit complex. It's not like traditionally we really easy just to use different slope to doing the job. Yeah.
All right, thank you. So we had a question from Anna come in that asked what literature you might recommend to someone who's a beginner with a background in spectroscopy or biophysics. In biophotonics or nanophotonics. Is there anything that comes to mind?
Literature, would you recommend? Well, there's lots of review paper and a really good review paper. I think in 2015, there's one published by Zhang Chen. If you're talking about the supervised one, there are many really great paper, because for these 5 years, this area is increased pretty fast. So have lots of good review paper. If you focus on to the like Nature is the journal or other journals, there are many review. So I would recommend just select this kind of review. But they're talking about spectroscopy and biophysics. So actually, yeah, there is lots of different. So biophotonics and nanophotonics kind of different. For nanophotonics, actually, there's really good book. I forgot the book's name, but it's discussed. I think, damn, I forgot the author of the book.
So I can connect you with Anna afterwards too.
Yeah,
and
so there's a really good book that covered everything about nanophotonics, and also even decrease a little bit about the supervised. And for biophotonics, the field is how can we use this one to photonic technology to the biology application. So I would recommend read lots of review paper as well. And for example, there's one really good paper talking about by the professor. What's that? Damn, I forgot her name. Yeah, it's from Europe. One really famous professor, is lady doing the optical trapping, and she mentioned how can you use this kind of different nanotechnology inside a cell and doing sensing and lots of things. So that kind of review paper also really helpful. Oh yeah, it's Lenny, yeah, and yeah.
All right, sounds like a good place to start. So we have one more question from Cyril that asks, can you briefly repeat the explanation for a stronger optical tweezer? And what's the wavelength you are using for the trapping?
Okay, so so that paper is still under review, and so I didn't show the figure here. But actually, it works for all rare earth elements. So it works for ytterbium, erbium, and neodymium. And for different elements, you need to use different wavelengths. For example, for ytterbium, because absorption is around 980. So if you so it's the trapping force is oscillation. So if you start from the 980 or 70 and end by 990, they all have force enhancement, but sometimes higher, sometimes lower. And the explanation of this one is because the resin is basically unresonant. So if you're familiar with the plasmonic effect, you may know that everything, if you shine a light onto some material, so you basically just trigger the resonance. So it's just like the differential equation, and like plasmonic similarly. So you're driving all the atoms inside, and you have the electromagnetic wave. You trigger this the resonance of these ions, and then your electric charge will be resonant. But this is dielectric resonant. And inside this resonant material, because have 4F energy, is a forbidden band. So it's like pretty much protect each of these ions, and each of them like individual one. Once they alternate, and this will give you extra response to your beam. And this beam just reflected to the suspectivity change. And if you have many, for this non-material, we have 2,000 emitters inside. And we have like the absorber can be even higher, like 5,000 something. So all of this is just like a resonator inside to enhance this response. And this one increase the force. Yeah. So it's a little bit harder to describe without a figure. Anyway, so and for the wavelengths, you need matching with the resonant condition, and you basically need to match the energy level. But you also want to avoid because you increase the real part of the polarizability, but you permittivity, or you also increase the imaginary part, but the imaginary part will absorb the light. So you want to off a little bit about the peak, absorption peak, but you still want to maximum the real part. Yeah.
All right, sounds good. Thank you. So that was our last question, and we'll wrap up our question and answer session with that. Everyone, please remember when you disconnect today, you're going to be prompted to complete a short survey. So if you could provide us with your feedback, it would be appreciated. You'll also find a link to the PDF copy of the slides on that survey page. And then we'll be emailing you within 48 hours to send you a link to the recording and the slides as well. So I would like to thank Van Wang for being here to present for us today. We very much appreciate it. And I'd also like to thank our Imaging Optical Design Technical Group for organizing this webinar for us all today. So on that note, thank you all for joining us today. This concludes our webinar.
Thank you, Susan. Thanks everyone. Have a nice weekend.
All right, everyone. Have a good weekend. Bye.
Bye.